Okay, and I'm on my laptop, so it might be kind of slow. I could not get WSL to run on my new motherboard on my computer. But okay, so hopefully y'all can see my screen. Um, this is just going over forking, like I said earlier. So um, that's pretty much it. Um, I'm gonna mute this person. Sophie, I'm gonna mute you. Okay, all right, thank you. Okay, so let's go ahead and start. I wrote some things down here. Um, these are just gonna be kind of here. I just wrote those down at the top of my head just so I don't forget them. Um, we'll get to this later. This is more for like theory if you really care, but it's not really, I don't think it's very necessary for the exam or anything. But starting off, let's first just go over an example. So this will be kind of what the extra credit will look like. Of course, it's not going to have this exact one. It might be two grandchild processes one grandchild process for process three, or one child process. Like it's going to be different numbers and different processes. So it's going to be different, but this will still be the same premise. It'll still be the same thing of like, you know, having as many grandchild processes as whatever. It's all the same, so you're not gonna have to worry about really the input too much. But we're gonna be building an example around this, and so yeah, we can just go ahead and start. So first off, you got to look at forking, and you got to look at pretty much what we're doing and processes and sub processes as like just look at the code itself. So if I structure this, the initial saying that I am the parent process, right? This is because we are the parent process. When we run this, I spelled process wrong. When we run this, this is initially going to be the parent process. At the start here, we're going to start at our parent process. And as we move in through our code and as we start forking, that's when we're creating sub-processes and child processes and stuff like that. So your first initial viewpoint should be looking at how many child processes we're going to make, okay? So in this case, we have one child process, two child process, three child process, and four child process, right? So because we're making 4 children in total, what we're going to want to do is we're going to make a loop, right? And we're going to say for integer I is equal to 0. And we could say I, is 0, and then we'll do less than 4, okay? And we will, and I guess we could just do this so it matches the input here. And so this essentially is just it's a basic for loop, right? And everything in this for loop will create a child process. So immediately after making this loop, we know that we can actually create a sub process because this loop is going to be run 4 times, and we're going to make 4 sub processes or child processes. So we can start by saying that there's 2 ways to do this, and I had some people question me on this earlier. I know Rincon does this where he goes PID is equal to fork. He does that, and then he checks the PID if it's 0. But you can also do just straight up, like you can do this if you want, or you could just do if fork is equal to 0 and cut out this middle band. It's completely up to you. He's not going to take off points. We're not going to take off points if you do this in your assignment or anything. So this is perfectly acceptable, or we can do the PID is equal to fork. What I'm going to do is I'm actually going to separate it because it's a little easier, in my opinion, for students to understand that this is the actual forking. So this is where we create the child process, okay? And then we'll check if PID is equal to 0. Now, again, I also had another question. Well, what is this and why are we checking if it's 0? So forking, this function itself, as soon as this function is called, it will create a child process, okay, from its parent process. So as soon as this is called, whether it's being attached to a variable or not, we have just now created a child process. And everything going forward theoretically is inside this child process. And you have to also understand kind of the concept that while that's going on, the parent process is still running simultaneously. So I guess I'll just draw it out. So we have like our parent process, right? And our parent process is going to keep going till the end of the program. And this is like as soon as we call wait, like right here, like let's say we call, or sorry, fork, as soon as we call fork, then that's when it like branches off and it's going to keep going. And let's say we call fork again right here, then it's going to branch off and keep going, but they're still going to keep going. Okay, so put that in perspective that all of these processes are still running simultaneously, but whenever you call fork, at that instance, at that point, is where it's actually going to be creating a child process. So if I were to put a print statement right here, like if I said see out hello or why does it do that? If I say like hello here, then it's only going to do this once because it's in the parent process. And as soon as we call fork, it's like think about the see out being right here and the fork is right here. So the fork isn't going to affect this. It's only starting from where it was called and going forward in the code. Okay. So that's a good concept you need to understand for when we get to the exits and the waits. And so you can better conceptually get what we're doing here. So, yeah, so here we're going to call fork, and this is where we do our branch. This is where we begin our next process. And we check if it's 0 because if it's 0, it means that the fork was successful. And it means that we can actually, it means that everything went well and we have successfully created this. It's just a good check to have. Theoretically, you don't really need it, but it's a good thing to help organize your code, and it's just something good to have. So yeah, as soon as this fork has been successful, we can now continue in here. And at this point, we have, after we've confirmed the child process, at this point, we are now inside the child process. Okay, so now we can see out I'm the child process. And of course, we also need to include these numbers, right? Keep in mind, we're still in a loop. So we can just say, I am the child process, and then we could just do I. Okay. So we are the child process for whatever I is, okay, which in this case is 1, for if we're going through this the first time. And so I know this is a little confusing, but again, think about this, right? We have just, this program, this parent program is going to do this 4 times, okay? It will for a fact loop through all of this 4 times. And it's going to create these child processes 4 times. And the processes are going to keep going, and that's why I is going to be important, because this will always change as I continues. As the parent process goes down the line, it will keep creating new and new childs. Okay. So we have our child process, I, and we've already taken care of this, we've taken care of this, we've taken care of this, and we've taken care of this, right? Very, very nice, very simple. Of course, there's still going to be a few things we're going to have to do, but we've already pretty much done most of the problem. So now, of course, we need to create grandchild processes. And these processes are going to be different for each number, right? Each given number. And there's ways to do this, of course. And so what I'm going to do for now is it's going to be kind of in ascending order. But what Rincon is going to give you is he's going to give you something like create 2 grandchild processes for this child and create 1 for this. And for that, I can show you how to do, but for now, it's just going to be the same concept, but it's not going to look like this, okay? So now what we can do is we can create a grandchild process, and that's, again, in my case, I'm just going to use a loop. And I'm going to say for j is equal to 0, and I'm just going to say while j is less than I, so whatever our current I is, and j++, okay? Now, before we move on and before we start creating grandchild processes, there is something that we have to understand. And I guess there's multiple ways to look at this. What I would say is every time you create an if statement, after you have confirmed the success of the fork, At the very end, make sure you put an exit 0. Okay. Make sure you have this underscore exit 0. And this is very important. If you don't have this under your if statement, after you've successfully created the fork, if you do not have this, your program will not run correctly. It will be all out of whack, and you will make so many child processes, so many grandchild processes, it'll be crazy. So make sure you always add your exit after your if statement, okay, or after your successful fork, okay. And so I'm just going to put that here just so we have it and so we understand it. I'm actually going to decrease this so we have more room. So I'm going to create another loop, and this loop is going to create more grandchild processes, and it's going to be the same concept. We can reuse PID, and we can just say fork. So at this point, I have just created another process, and this process is beneath this fork, meaning it's a grandchild process. Okay. And now we need to, of course, check, is this successful? Did we successfully make this grandchild process? Meaning if PID is equal to 0, then that means we have successfully done this. And we can see out, now that we've successfully done it, I am the grandchild process for, and then we could just do, we'll just do I. Okay. Right, so we have done that. And again, what do we do after we do the if? What goes after the if? We need the exit. Okay, so we need the underscore exit 0. Always going to be at the very end, outside or inside the if statement. Okay, and I'm going to go over why exactly what the exit does and why we need it. But for now, just keep in mind that this is why this is very important. Okay, after every if statement, after every successful, add an exit. Okay. Now there is one more thing we have to do, and technically this is done. This is all you have to do. Very easy, right? But there is still one more thing we have to do, because if I were to run this code right now, I'll give it a run. Well, let's look and see what happens here. We have, I'm the parent process, I'm the child process for 2, I'm the child process for 1, for 3, grandchild for 2, grandchild for 1, grandchild for 2. Look how out of order that is. That's whack. That is not correct. And the reason, and if I run it again, it'll be different. It'll be different every time. Look at that. This time it didn't even make a grandchild process. What's going on here? The reason is that you have to keep in mind, when we're running everything simultaneously, it's kind of like a race, right? Our operating system is trying to handle all of these processes, and instead of having them in an order we want them to be handled in, it's just saying, look, first come, first serve, right? If this process finishes before this one, then it's going to print out whatever it was going to print out. If this one finishes before these, it's going to print out, right? And so it's very inconsistent, and this is what messes up a lot of students, is even if they understand the fundamental code of forking and whatever, if you don't include a command I'm about to show you, then you're going to get a really messed up output all the time. So how do we stop this? How do we keep consistency? Well, we do something called waiting. And these waits have to come at the very end of your loops, okay? They have to come at the very end. And it's the same concept of inside your if statements with an exit, okay? So if we have this first while loop here, then all you simply have to do is call wait and then null pointer, okay? And what this does is this essentially tells the parent function, this tells this parent process, says, hey, look, you're going to wait until everything above you is done processing. And there's nothing above the parent process. So you don't, we'll still need this, but this ensures that nothing can come before the parent process and everything will happen after the parent process. So if I run this, we will see that it may still be out of whack, but you'll most likely see that the parent process always comes first, right? It always comes first because it's saying here that this loop has to wait for this parent process to finish. It's saying that, hey, look, this line, this parent process needs to be done before any of this can even think about finishing. This can run, this can execute, this can do everything they want to do, but before it's declared finished in the operating system, it needs to wait, okay? And now all you have to do is apply that same concept to your other loops. And our other loop is just this one other loop in this case. And so at the very end of your loop, all you got to do is just say wait, null pointer. Okay. And now if we run this, this will be consistent every time. We see we have the parent process, we have child process one, and we have two grandchilds. We have two, and then we have three grandchilds, three and four grandchilds, four and five grandchilds. And of course, this is because I made this little if, or this little function here, okay, or this little for loop of j is less than I, and j is always 0, and as I is increasing, so is j, so it's technically increasing the amount of processes. And I can run this an infinite amount of times, and it will always be the same output every single time, okay? And that's it. This is the main understanding of forking. Now, again, like I said, he's going to give you an instance of, well, what if I want grandchild process what if I want child process one to only create one grandchild? Well, then all you have to do is you can edit your loops. So we know, again, from the count that we're still going to have 4 children. But if we want, let's say we want only process one to have one grandchild, okay? Then what we do is we just check if I is equal to 0, right? Then we can go ahead and fork. Okay, so if I is 0, or sorry, if I is 1, meaning that this is the first child process, because it's all in the loop, if I is 1, then we can do fork again, and we can just say if PID is equal to 0, right? If this is successful, then we say I am the child process, right, of 1, so for 1. And then, of course, don't forget your exit, like that. And it's that simple, okay? That's it. That's all you got to do. And then, of course, we can do like an else. We'll need this else here, because otherwise this is going to like always do that. But in this case, like, there we go. So now if I run this, you'll see that we only have one grandchild. Sorry, I meant grandchild. We'll see we only have one grandchild process for the child process one every single time, right? So if he gives you something like this where he says on process 3, I want 2 grandchild processes instead of whatever, then all you got to do is just do the check of I. So if I is equal to 3, then make a loop. You can make a loop, and you can, make it 3 grandchild, whatever. Okay, but this is the key right here. This is the key to having specific amount of grandchild processes for whatever process you're going to want to make a sub process for. Okay. Now, if for those of you that may have been really intuitive, you may have asked, well, why do we not put a wait, right? Why is there not a wait here? And that's a good question. We actually don't need a wait for this because a waiting is, you could say, is subjectively applied to loops, right? Because you got to remember, whenever you fork, again, this is the instance in which we have branched off, right? So let's pretend that this fork here is this process right here. We know that this process is going to print out because we've already said right here that it needs to wait for this to be done before any of this can be done. Okay? So essentially what I'm saying is you're really not going to need waits for grandchilds. Okay? You're really not, because this wait is already taking care of the rest of the processes, and this wait is saying that this needs to be done before this can be done. And this can't be done unless this is done, right? So, I'm sorry, opposite. This can't be done unless this can be done. So that's why we don't technically need a wait right here, is because there's no possible way this gets reached until this child process has been finished, which we've already declared with this wait that has to wait, that this can wait until this is fully done. Okay. And I know it's a little confusing, but and if you have questions, I'm about to give you as much time as you want to ask me and to talk about it. But this is everything you need to know. This is pretty much the entire thing. I will, again, have this video uploaded so you can rewatch it. And I'll also paste this code in resources so you can take a look. But yeah, okay. Now, if anybody has a question, feel free to ask. Other than that, that's pretty much it.
Hey man, how do we use the terminal to check our processes again?
Um, so it just depends on your IDE. Make sure you have to have WSL, or you have to have a subsystem like a Linux or whatever. Um, so I guess in my IDE, I can choose that. I can go to my tool chains and I can say I'm using WSL, and then I can run it. So these are your includes. This is the most important one here, but it just depends on your um, IDE, honestly.
If I'm using a bash terminal in VS Code.
A bash terminal in VS Code, you have to make sure that VS Code is being run through WSL, and you would just do like, um, just do like G++, and then, well, you would CD to wherever your file is. So in my case, I'm already here at Forking Review, or I could just CD my main, and then, I guess not. I guess I'm already in here. I can't
I'm
CD to
sorry, I
that.
think I didn't explain my question well. I
Oh.
meant like how can we view like all active processes so we can see like the parent, like make sure
Oh,
we're
oh, oh,
actually
oh. Yes, yes, yes. Okay, I see what you mean. Oh, like how Rincon does it when he pulls them up?
yes, sir.
Yeah, yeah, yeah. Okay, that's a good question. I actually don't know how. What you can do, I don't know how to display it in the terminal, but I think what you could do is you can actually print some data about the ID you're in. I would say you could probably do. Well, PID is just an integer. Is there any subcommands for fork? I don't think so. I'm sure you'd have to look up like some C++ thing that's like how to view current, like how to print out your current uh, ID for what process you're in. And then you would just print that below, or sorry, inside your if statements. And that way you can view it. I don't know how to actually view it from the terminal like he did it, though. I'm going to be honest. That's a good question.
Okay, that helps though. Thank you.
Yeah. If you don't have that, I would just recommend printing out your current data based on wherever you are in the code. All right.
Um,
Any other questions?
Sorry, one more thing. So on the test, I think he said he wants us to call wait in the loop, right? Even though that wouldn't really be multiprocessing at that point. I might be misremembering that. Maybe someone else can back me up.
Yeah, you do need to call wait in the loop. Correct. But it's not so. Yeah. So the thing is, this is multiprocessing, but it's in a different system than multi-threading, right? And I kind of wrote that down here. Threads share memory, processes don't. So threads are more of like, I guess I'm a better visual learner in my case, but I guess threads are more like you take your process, and then you take another copy of the process, and you take another, and then you execute them, and then you print them out in the order in which you want to print them out. Whereas thread or forking is doing this. It's like a ladder. It's like a tree actually. It's like a tree of different processes. And while the wait could technically, you could argue that the wait is making it inefficient, right? Like, what's the point of doing this if you're just waiting on the process before? Why not just use a regular loop or whatever? And that's fair, but I think it's still better to understand the concept of creating sub processes using the parent process, because that's the one thing you can't do with threads. What you can't do with threads is take, it's all or nothing with threads, right? You're taking either the whole parent thing and messing with it, or you're taking none of it. Whereas forking can create child processes from the process above it, which inevitably saves you and can save you some memory. Or sorry, which actually expenses memory, but it can save you more time with executing things in some scenarios. But yes, you always do need this wait in the for loop here. And again, that is for consistency reasons, for output consistency. But if you were doing like something that, the output doesn't matter, like if you like don't care the order in which an output is being put in, you could ignore these weights, and technically this forking would be a lot faster. Yeah. So, anything else?
I have a question.
Yeah, what's up?
So for tomorrow, is he gonna give us the screenshot from the terminal where it shows PID, UID, or is he gonna give us the output?
He's going to give you both. He's going to give you this, and he's going to give you the terminal screenshot. And he's also going to give you example code. He's going to give you code that kind of looks like this, actually. So you really need to just kind of understand this little middle part. You basically, I'm telling you right now, you need to understand this little if I is equal to 1 or if I is equal to 2 and understand how to make grandchild processes for different number processes. This is what you're really going to need to understand because he's going to give you a lot of this. But yes, to answer your question, he will give you the terminal and he's going to give you the example output that he wants. You'll have both.
Okay, can you go over how we can read the parent and the child from the terminal screenshot?
Sure. Let me. Does anybody have a screen? I can pull that up real quick. But if anybody has a screenshot of the terminal, that would be nice if they have it on hand. But let me see if I can grab it real quick. I'm gonna have to go to probably. I can only get it from the exam or the extra credit, and I don't obviously want to do that. I guess I could draw an example. Might do that. Let me draw y'all an example here. Okay, perfect. I see.
I think there's one on the practice exam. I could get that.
Oh, there is? Okay, perfect. Let me go look at the practice exam. Okay. Oh, yeah, I see it here. Okay, let me copy this. I'm going to paste this in the Discord so I can convert it to my my laptop here. Okay. Let's take a look. Oops, don't mean to click that. All right, so okay, so this is his bash terminal, right? This is what I think. Hopefully, this is spaced out nice enough. So yeah, let's take a look here. So first off, you can see that UID is 501, and this is meaning that the process in the CPU or in your operating system in 501, that's like consistent. So that just means that think of this as your consistent parent process. This is the program you're running, and this is the way the computer tracks overall what you're doing. Okay. Your PID though is different. You can see it's very different, and it's hard to find consistencies in here because these are different and the PPIDs are different. And I know it's also confusing because I had somebody come talk to me during office hours today. Rincon, for some reason, he likes to name this PID, is equal to fork. And I actually don't fully understand why, because the PID, in this case, fork is only returning 0 or 1. It's not returning the actual PID of the process you're creating. So why he names it PID, I don't fully know. That's a good question to ask him. But I would say whenever you're looking at these, obviously these numbers don't mean anything because they are different for every person, for every operating system. So what you need to pay attention to is the unique numbers, right? The amount of unique items there are in these columns. So we see 18282, that's 1. 18360, that's 2. 18419, that's 3. 18420, that's 4. 5, 6, 7. So we see that they're all unique. Okay, they're all unique. So we know that this many processes are being developed from this parent UID. So we know that 1, 2, 3, 4, 5, 6, 7, 8 processes total are going to be made. And if I look at the, oh wait, actually that's not right. Hold on, I'm looking at the example here that y'all have. I'm the parent process. Okay, wait, that's not right at all. Okay, well, honestly, I don't really know then, because these should be unique per. Yeah, so 8. Yeah, there we go. So 18419, 18419, 18419, 18421, 18412. Oh, I'm actually gonna. Oh, never mind. Okay. That's a good question. I actually don't know how I identify it. I guess the way I used to do it doesn't match with the example that he gave this with. Because in his example, you have a parent process, you have a child process 0, a child process 1, and a grandchild of 1, and then you have a child process 2. And if you don't know what I'm referring to, I'll just paste it right here. So, this is correlating to this. I actually don't know. I mean, you're gonna have to ask Rincon about that. The only thing I can really assume is that the uniqueness of the numbers. We see that 1, 2, 3 are the same, and we see that the rest are unique. So I'm gonna be honest. I don't know how to. I guess the way I thought it was is not right.
It looks like 19 is the parent process, and then 20, 21, 22 are the children process, and then 23 is the grandchild of 21 or whatever, however you want to say it.
So you're saying that this is the parent.
No, 8419 is the parent.
Oh, okay. Yes, because it's having 3. Yeah, it's having 3 instances of itself, which is these child processes. I see. And then, yeah, so I guess the order in which they're put in is not going to be in the order in which the output is, because I would have assumed that this is up here. But I guess when I took this class, I didn't do this. I just followed whatever the output was. And I attended a lecture one time where he talked about this, but I guess I didn't really grasp it that well. But yeah, I mean, like he said, you can take, I guess because of these 3 unique
It's
processes here.
also, if you look at the very end, it says PQ1. I think that's how you know those like 5 at the end, far right of the where it says time
Oh, I see.
CMD. Yeah. So those,
Yeah.
that's how you know those 5 are for that question. I think as well.
Oh, smart. Okay. Well, there you go. Yeah, you guys teach this part. I don't know this part. So yeah, if you look at PQ1, you could see what file it's in. And you could say, well, PQ1, we have we see that there are these same here. So 3 parents are being copied, and then we have 2 unique. And I would assume that, I mean, you can't tell what order. You can't say that this is the grandchild and this is the parent, but that's what I would say. You could say that this is the parent, these are the children, and then this is the grandchild. I don't know.
If you look at PPID, it'll tell you who its parent is.
Oh, parent process ID. Well, there you go. Yeah, that makes sense. So yeah, I guess just identify, based on what y'all have said, identify the make sure it's in the proper file, I guess, and then go over here, and you could work your way backwards if you wanted. You could take the PPID does stand for parent process ID, and then PID stands for process ID. And so you could take a look and you could say, well, we see that the parent shares the same parent for these 3, and it has a unique parent on this one and a unique parent on this one. And we can see that, I guess the order does matter, because then if this is the parent that's being copied or forked 3 times, then we see that this here is the parent. It's being forked 3 times, and we know that because of this, because the parent ID is right here. It creates 3 child processes, and we see that child process, or there's a grandchild after child process 1, and we see that the parent of this one, 18421, 18421, is process 1, because this is parent, this is child 0, this is child 1, child 2, grandchild. So yeah, there you go. You guys solved that. I didn't even do that. So I guess to sum up, take a look at here, make sure it's in the right file. Then this is the parent. This tells you where it came from. and this tells you its current ID. And my best advice, I guess it is still from top down. So I would just work backwards. See, 3 have the same parent. 1 is unique, 1 is unique. Find the parent, see that, and you can coordinate. So if you want to do it that way, now you know from your peers. But if not, just take a look at this. It will tell you. This also tells you what I to, this tells you specifically I at 0, at I0, nothing. At I1, check if I is equal to 1, then create a grandchild, right? If I is equal to 2, don't create a grandchild. Kind of how we showed earlier here. So yeah, good job, guys. You guys are smarter than me. You figured that out. So, alrighty. Any other questions?
I have a question.
Mm-hmm.
So if it was like if I is equal to 1 and it wanted to do like 3 grandchilds, would you just call fork 3 times?
No. So if you call fork 3 times, that's essentially doing this, like fork, and then fork, and then fork. It's like that's creating a parent, child, grandchild, great grandchild, great great grandchild, right? So if you want to create multiple processes, you have to do the loop, right? So let's say you want say if I is equal to 1, right? And we need to make 3 grandchild processes for I. Then we can go ahead and delete this. And we got to create a new loop. So I'm just going to copy this loop. And I'm going to say fork, check if it's successful. And then we can go ahead and say I am the grandchild process for I. And we have to change the loop, right? So you wanted 3, right? So we'll just do 3. And then you would fork, right? So create your loop. Check, is I equal to 1? Yep. Create your loop. Fork. So we're going to fork however many times are in the loop. And if that's a successful fork, go ahead and print out, hey, we did it. We're here. And exit. Oh, I never really explained the exit. I meant to do that. I'm so sorry. The exit, this might answer your question too a little bit on this. The exit ends the process. This is like, think about it as like a return statement, except instead of returning, it straight up just is done with the process. Like it finishes the whole piece of code. Okay. And we have to exit as soon as we print this out. Because if we don't, let's say we don't have this exit, this process is going to keep running. Because technically what's happening here is that this is a good graph, but a better one would be to say what's actually happening in the code is that you have your parent, and then you have your fork, and then you print out right here, and then you close it, you stop it right there. After you've created it and printed it out, that's the exit. Okay? And then before we call exit, that's how we make a grandchild. Let's say this makes a grandchild. Then before we call exit, that's why we make a grandchild. And then we print out, hey, I'm a grandchild, and then exit. Okay? So that's what this does. This prevents the process you just made with fork from going on and on and on and on. Because otherwise it doesn't know when to stop. It's not just going to stop after printing itself out. It's going to keep going. It's going to keep this loop going. It's going to access this loop. Because it's just a copy of this entire code. You got to remember that. It's a copy of the entire code, except it starts where it's been forked. Okay? So, if you wanted I to be 0, I to be 1, and you wanted to make a certain amount of grandchilds, you just say, well, if I is equal to 0, make a brand new loop, call fork. Is that a successful fork? Awesome. Print out you're the grandchild for I, exit, make sure you wait to make sure that these print out at the same time. And if we run this, you'll see, there we go. We have 3 grandchildren process for 1. Okay? Does that answer your question?
Yes, thank you.
Okay, no problem. Okay, I'm going to end the recording.